Hello everyone, my name is Amit Chaudhary and here we have topic of organic chemistry which is alkene. As seen here, we will see some rules governing reactions and we will also see intermediates generated in particular reactions with mechanisms, and we will also see transition states. Content includes definition of alkene, structure where we will see sp2 hybridization in carbon, isomerism, stability of alkene, general methods of preparation of alkene where we will see 1,2 elimination in detail. In general reaction, we will see detailed reaction of electrophilic addition, free radical addition, hydroboration oxidation and ozonolysis. Within this content, we will study rules like Saytzeffs orientation, Hofmann orientation, Markownikoff and anti-Markovnikov orientation. We are also going to see some terminologies like heat of hydrogenation, steric repulsion, carbocation and its stability, regioselectivity of reaction, stereochemical aspects in reaction. Definition of alkene: it is acyclic branched or unbranched hydrocarbons having one carbon-carbon double bond, and general formula is CnH2n. Simple meaning of alkene: it is hydrocarbon that contains carbon-carbon double bond. However, an acyclic branched or unbranched hydrocarbons having more than one double bonds are called as alkadines or alkatrines depending on number of double bonds present in compounds. Synonym: alkene is also called as olefins, means oil forming compounds, or alkylines or unsaturated hydrocarbons. General formula is CnH2n. The important part of structure is sp2 hybridization of carbon. For this, we have to see valence shell electron configuration of carbon. Here is the ground state electron configuration. This indicates energy level, where outer shell contains 4 electrons, out of which 2s contains 2 electrons, 2px and 2py have 1 electron, and 2pz is empty p orbital. For hybridization, carbon first reach to excited state where there is migration of electron from lower orbital to higher orbital. Here one of the electron of 2s orbital jump to 2pz orbital, and here is the excited state electron configuration of carbon. After this, there is mixing of 3 orbital where participating orbital are 2s, 2px and 2py orbital gives 3 sp2 hybridized orbital. Here we have one of the unhybridized 2pz orbital, and these hybridized orbital have intermediate energy level between p orbital and s orbital. So this is the sp2 hybridized state of carbon. Orbital shape and arrangement of orbitals, where this yellow color indicates sp2 hybridized orbitals and here is unhybridized p orbital. When we see side view, these hybridized orbitals lies in same plane and unhybridized orbital lies perpendicular to hybridized orbital plane. Top view, we can see bond angle between hybridized orbital is 120 degree. We know in sp2 hybridized orbital there is one s and 2 of the p orbital. So 33% part is of s orbital and 66% part is of p orbital. So sp2 hybridized orbital has 33% s character and 66% p character. Molecular representation of ethene. Here we can see orbital overlapping, where separately we can see here sp2 hybridized orbital are participating to form sigma bonds. Here there is sigma bond between carbon-carbon. Here is the carbon and hydrogen. P orbital overlapping gives pi bond. Here is the ball and stick model for ethene. We can see the sigma bonds means sp2 hybridized orbital lies in same plane, and here is p orbital which is perpendicular to hybridized orbital plane. In alkene we can see geometrical isomerism, which is represented as cis and trans. For alkene, if hydrogen on same side, it is called as cis isomerism, while if hydrogens attached with this sp2 carbon are on opposite side, it is trans isomer. To draw a molecule, we have different kind of structures like condensed structure, where we are representing carbon and hydrogen with bonds, while to draw more clearly we have skeletal structure, where we do not need to represent carbon and hydrogen. Here carbon-carbon bond is represented as line. Here is the sigma bond and here is a representation of double bond. So here is two type of structure of cis 2-butene. For macromolecules like prostaglandins, this skeletal structure is better representation for molecule. Here in prostaglandin E2, there is a chain which have two type of alkene isomer. Here is cis alkene while here is trans alkene. Stability of alkene. For this we need to see heat of hydrogenation, which reveals relative stability between alkenes. First we will see relative stability of cis and trans isomers. Examples with hydrogenation of butene. Trans 2-butene upon hydrogenation with hydrogen gas in presence of palladium catalyst gives N-butane with heat of hydrogenation which is 27.6 kilocalorie per mole. Cis 2-butene upon hydrogenation gives N-butane with heat of hydrogenation, that is 28.6 kilocalorie per mole. We can say as trans 2-butene evolves 1 kilocalorie less energy than the cis isomer. So it contains 1 kilocalorie less energy. So trans isomer is more stable by 1 kilocalorie than cis isomer. We can see here more clearly as this cis isomer upon hydrogenation evolves 28.6 calorie and converts into butane, Here trans isomer evolves 27.6 kilocalorie and converts into butane. So the difference between these two isomers is 1 kilocalorie, and here energy of this trans isomer is less than this cis isomer. The difference is 1 kilocalorie. One of the comment which is trans isomer is more stable than cis isomer in alkene. For this we have an example of 2-butene. Here is cis isomer and here is trans isomer. If you see in cis isomer, both methyl group lies in same side, so they are nearer to each other, while in trans isomer they are far apart. When we see electron density map of 2-butene in cis isomer methyl group, as they are on same side, there is overlapping of electron cloud is there, so there is more crowding, so there is more repulsion in cis isomer, while in trans isomer, as both methyl group are on opposite side, they are farther apart, and therefore there is less crowding, and thus there is less repulsion between bulky groups and less van der Waals strain. Therefore, trans isomer is more stable than cis isomer. Relative stability of structural isomers. For this, we will first see substituents in alkene. Normally, these sp2 hybridized carbon of alkene are joined with alkyl substituents. Alkyl group which is attached with sp2 hybridized carbon is called as alkyl substituents. Here is the example where methyl group is attached with sp2 hybridized carbon. Normally, alkyl substituent is denoted as R group. Now, coming toward sets of example, here first set is of butene, where we have two structural isomer. Here is the example of geometrical isomerism. First isomer have heat of hydrogenation value, it is 30.3. Here cis isomer have 28.6, while trans isomer have 27.6 heat of hydrogenation, and these examples we have seen previously. In second set, example of pentene, first isomer have heat of hydrogenation value 30.1, second isomer 28.6, and likewise we have possible structural isomer with their heat of hydrogenation values. We can see in set 1 these structural isomer have highest heat of hydrogenation value, these have lowest heat of hydrogenation value, and in set 2 these isomer have highest heat of hydrogenation value and these isomer have lowest heat of hydrogenation value. Now, what is the difference between these structural isomers? Here it is less substituted alkene, this is more substituted alkene. In this example, there is 2 methyl group present in alkene, so it is disubstituted alkene. While in this example, this sp2 hybridized carbon have only hydrogen, there isn't any alkyl substituent. While in this carbon, there is ethyl group is there as an substituent. So because it have only one substituent, it is monosubstituted alkene. This alkene is because it have 2 methyl group, means 2 alkyl substituent is there, so it is disubstituted alkene. Disubstituted alkene, monosubstituted alkene means more substituted alkene and less substituted alkene. And likewise we can see in set 2, here there is only one substituent. There is 2 hydrogen, third hydrogen, and here is alkyl group. So it is monosubstituted alkene, and here 2 methyl group, third methyl group means 3 substituent is there. So it is trisubstituted alkene. In this example, we can see more substituted alkene have lesser heat of hydrogenation value. So more substituted alkene are more stable than less substituted alkenes. From previous example, we can conclude as the stability of an alkene increases as the number of alkyl substituent bonded to its sp2 carbons increases. So most stable alkene is tetrasubstituted alkene. Then there is trisubstituted alkene, then disubstituted alkene, monosubstituted alkene, and least stable alkene is unsubstituted alkene, which is ethene. Next is the preparation of alkene. First example is alcohol are heated in presence of acid, which gives alkene. Second reaction, Hofmann Elimination, where quaternary ammonium salt are reacted with silver oxide in water, which liberates hydroxide ion, which eliminate hydrogen and this quaternary nitrogen, which gives alkene. Third reaction, which is elimination reaction, which is also called as dehydrohalogenation reaction, where alkyl halide in presence of alcoholic base gives alkene. Next reaction is dehalogenation, where vicinal dihalide reacted with zinc in alcohol gives alkene. Last one is cracking, where cracking of alkane also gives a product of alkene. Here is the example where alkyne are converted into alkene by hydrogenation reaction and reduction reaction. In first reaction, alkynes are reacted with Linder's catalyst in presence of hydrogen gas gives cis-alkene. It is the example of catalytic hydrogenation. In second reaction, alkynes are reacted with sodium in ammonia, which is dissolving metal ammonia reduction, and it is a named reaction called as Birch reduction, where we are getting trans-alkene. Next is Wittig reaction, where aldehyde or ketone reacts with triphenyl phosphonium halide to form alkene. Here is the interchange of doubly bonded oxygen of carbonyl group with doubly bonded carbon phosphonium halide group. From these preparations, we will see 1,2 elimination in detail. What will happen when alkyl halide is reacted with electron-rich species? One of the possibility, that is substitution reaction. It is the reaction where the electronegative atom or electron withdrawing group is replaced by another atom or group. However, there is second possibility, which is elimination reaction. Elimination reaction is the reaction where the electronegative atom or electron withdrawing group is eliminated along with a hydrogen from an adjacent carbon, and here we are getting alkene as product. General reaction where alkyl halide is reacted with base gives alkene, conjugated acid of this base, and leaving group. Other name of 1,2 elimination is dehydrohalogenation, 1,2 elimination, or beta elimination of hydrogen halide. Why it is called dehydrohalogenation? Because this reaction involves removal of hydrogen and halide from substrate. Why it is called beta elimination or 1,2 elimination? Because two groups are lost from adjacent carbon atoms. Kinetic duality of mechanism is explained by Hughes and Ingold experiment. In their experiment, they have taken low and high concentration of base and reaction performed using primary, secondary and tertiary alkyl halide. We know alkyl halide when reacted with base gives alkene, and in experiment they examined various reactions of alkyl halide with strong base. Their observation were main thing they have noted that at low concentration of base rate only depends on alkyl halide, and at high concentration of base rate depends on both alkyl halide and base. So at lower concentration of base order of kinetic is first order. At higher concentration of base it follows second order kinetic. At different alkyl halide, primary, secondary and tertiary alkyl halide, upon high concentration of base they follow second order kinetic, while secondary and tertiary alkyl halide at low concentration of base they follow first order kinetic. From this experiment, the conclusion is first order encountered only with secondary and tertiary alkyl halide at low concentration of base. As there is duality in mechanism, that is first order and second order, there is two type of elimination mechanism is there, which is named as E2 and E1. First we will see E2 mechanism. It is single step mechanism where abstraction of hydrogen by base and simultaneously leaving of halide ion. Both CH and CX bond breaks with formation of double bond in same step. Here energy of new pi bond formation is obtained from breaking of carbon hydrogen and carbon halogen bond. Potential energy diagram of E2 mechanism. In energy diagram, x-axis is progress of reaction, y-axis potential energy. Here are starting materials and here product, and hill represent transition state arrangement where there is partially bond making and bond breaking process is there. Now negatively charged base shift electron toward this hydrogen and form bond, so there is partially bond making process is there with delta negative charge on base, as base is using electron to make this bond. Simultaneously partially breaking of carbon hydrogen bond where bonding electron are taken up by this carbon, which this carbon used to make double bond, and here this carbon halogen bond breaks where bonding electron are taken up by this halogen. So in transition state halogen contains delta negative charge. Kinetic of E2 mechanism, it is single step mechanism. So we have single transition state where both reactants are participating. Thus rate of reaction depends on both reactants, alkyl halide and base. Therefore it is bimolecular reaction, as two molecules, that is alkyl halide and base, involved in transition state. It is bimolecular reaction, hence it is E2 elimination bimolecular reaction. Both reactant involved in rate limiting step, therefore reaction follows second order kinetic. Evidences for E2. For evidences, we need to see what is happening in mechanism of E2. Here, it is a single step mechanism where CH bond breaks and CX bond breaks. We have some of the evidences where reaction follows second order kinetic. It is not accomplished by rearrangement, not accomplished by hydrogen exchange, which proves it is single step mechanism. For CH bond breaks, this E2 shows a large hydrogen isotope effect. Another evidence, that is, it shows a large element effect. These evidences we will see in next slide. First evidence, reaction follows second order kinetic, as experimental data shows that both alkyl halide and base participate in rate determining step. Reaction follows second order kinetic. Second evidence, E2 not accompanied by rearrangement. As we know, E2 is one step, means concerted reaction, so there isn't any chance for rearrangement. Third evidence, E2 show a large hydrogen isotope effect. Isotope effect means difference in rate due to a difference in the isotope present in the reaction system. For example, we have 2-phenyl ethyl bromide where this carbon contains hydrogen. A labeled molecule of 2-phenyl ethyl bromide where carbon have deuterium in place of hydrogen. So at that time, deuterium kinetic isotope effect is equal to rate constant for hydrogen containing reactant divided by rate constant for deuterium containing reactant. Principle behind this hydrogen isotope effect is, if this CH bond is broken in rate limiting step, replacement of this hydrogen with deuterium will affect the rate of reaction. We know deuterium is heavier than hydrogen, so carbon deuterium bond breaks more slowly than carbon hydrogen bond, and this will create differences in rate of reaction, which gives deuterium kinetic isotope effect. First, 2-phenyl ethyl bromide is reacted with base and KH value was calculated, and then labeled 2-phenyl ethyl bromide is reacted with ethoxide base and KD value was calculated. Result which was obtained, that deuterium kinetic isotope effect is equal to 7. That means the rate is 7 times decreased in labeled substrate. Conclusion was, as carbon hydrogen bond variation affect to the rate of reaction, this beta carbon hydrogen bond must be broken in the rate limiting step. Fourth evidence, that it not accompanied by hydrogen exchange. For this, we have possible mechanism where hydrogen exchange is possible is of two-step mechanism, where in first step base abstract this hydrogen which gives carboanion, and then this carboanion use its electron to make double bond, and simultaneously removal of this leaving group gives alkene in second step. This two-step mechanism is seen to be even CB reaction. Here is the example where hydrogen is abstracted by this base, gives carboanion, which is further stabilized by this carbonyl compound, and then in step 2 there is removal of leaving group, gives alkene. Here is alpha beta unsaturated carbonyl compound as a product. Here it's a unimolecular elimination conjugated base. Now in our example we can also say as this base abstract hydrogen from here, so alkyl halide behave like acid and gives conjugated base, and simultaneously this base abstract hydrogen and gives conjugated acid. So reversible reaction also possible where this conjugated base carboanion regain its hydrogen and convert it into starting material. So step 1 is reversible. Hydrogen is regained by carboanion. It's a conjugated acid-base pair. Now to prove whether E2 is two-step mechanism where hydrogen exchange is possible or not, there was experiment performed where alkyl halide was 2-phenyl ethyl bromide, base was sodium ethoxide, solvent used labeled ethanol, that is deuterated ethanol. In reaction, phenyl ethyl bromine reacts with ethoxide ion which gives carboanion, and this ethoxide ion converts into ethanol. And the second step, that is removal of this leaving group, gives alkene which is phenyl ethylene. Now we know it's a conjugated base, so there is chances that it can grab this hydrogen and convert it into this starting material, and simultaneously there is also chances because we have used deuterated solvent, so this deuterium is abstracted by this carboanion and there is formation of labeled haloalkane as byproduct. So chances of carboanion formation as an intermediate is there. There is always formation of labeled haloalkane in reaction mixture, and again conversion of this haloalkane into carboanion is also possible. So if a reaction follows two-step mechanism by reversible carboanion formation, it would accompanied with phenyl ethylene and labeled haloalkane side product. Now observation of half reaction completion where only unlabeled 2-phenyl ethyl bromide was observed. There is no formation of labeled haloalkane. That means reaction not accompanied by hydrogen exchange, no formation of carboanion, and therefore this E2 is not of two-step mechanism. Fifth evidence that E2 show a large element effect. The reaction rate increases when the leaving group is changed from fluorine to chlorine to bromine, is called the element effect. We have example of alkyl halide, alkyl fluoride, alkyl chloride, alkyl bromide and alkyl iodide. Fluorine has smallest diameter from halide, and therefore this carbon fluorine bond is strongest bond from all alkyl halide, while in alkyl iodide, because iodine has longest diameter from all halide, this alkyl iodide bond is weakest. So bond strength decreased from carbon fluorine bond to carbon iodine bond. And as bond strength decrease in this direction, energy needed to break carbon iodine bond is lesser than carbon-fluorine bond. So what will be the effect in rate of reaction? As from alkyl fluoride to alkyl iodide, less energy needed to break carbon halogen bond, rate of reaction increased. Change in reaction rate upon changing the element indicates carbon halogen bond is broken in rate limiting step. It means when you perform a reaction using alkyl chloride and you are performing second reaction using alkyl bromide in same reaction condition, and if both reactant are giving different reaction rate indicates carbon halogen bond is participating in rate limiting step. And to know this, experiment was performed using different alkyl halide with same condition, and experimental result was obtained. The reactivity of alkyl halide toward E2 is alkyl iodide is most reactive and alkyl fluoride is least reactive. It means there is variation in reactivity toward E2 of different type of alkyl halide. So it proves that this carbon halogen bond effect on reaction rate, as there is different in reactivity of different type of alkyl halide, and therefore carbon halogen bond breaks in rate limiting step. Orientation and reactivity of E2. For this we have an example of reaction where 2-bromobutane is alkyl halide and base is potassium hydroxide. Now as it is E2 reaction, base abstract beta hydrogen and simultaneously removal of bromine from molecule gives alkene. For abstraction of beta hydrogen in 2-bromobutane we have 2 beta carbons. This beta carbon, carbon number 1, contains 3 hydrogen, while this beta carbon noted as third carbon have 2 hydrogen. So our base have 2 choice to abstract hydrogen. If base abstract hydrogen from this carbon number 1, you are getting 1 butene as product, and if this base abstract hydrogen from carbon number 3, it will form 2 butene. Practically both products are formed, but 1 butene formed with 19% yield and 2 butene produced with 81% yield. Major product is called as preferred product. Here preferred product is 2-butene, which is disubstituted alkene, and minor product is 1-butene, which is monosubstituted alkene. So here preferred product is which is more substituted alkene, as disubstituted is more substituted than monosubstituted alkene. Regioselective reaction is the reaction yields a mixture of isomeric product where one isomer formed predominantly, and here in E2 reaction we are getting 2 type of isomer but one isomer formed predominantly. So E2 reaction is also example of regioselective reaction. E2 orientation is also called as Saytzeffs orientation. Alexander Saytzeff gave a rule for governing orientation of 1-2 elimination called as Saytzeff rule, or in some references you will see Saytzeff rule or Saytzeff rule. Statement is, in dehydrohalogenation the preferred product is alkene that has the greater number of alkyl group attached to the doubly bonded carbon atom. Similar statement, In dehydrohalogenation, hydrogen is preferentially eliminated from the carbon atom with fewer number of hydrogen atoms. Predominant product or more formed product is called as Saytzeffs orientation or Saytzeffs product. In our example, 2-butene is preferred product. It is disubstituted product and isomer is monosubstituted. So this disubstituted product has greater number of alkyl group than monosubstituted product. So it's a preferred product according to Saytzeffs rule. And when we see reactant, it has 2 beta carbon atoms. And the statement abstraction of hydrogen from carbon which have fewer number of hydrogen atom. This carbon has 3 hydrogen and this beta carbon has 2 hydrogen. So base will abstract hydrogen from this carbon which have fewer number of hydrogen atoms. Greater number of alkyl groups in alkene, we have monosubstituted, disubstituted, trisubstituted to tetrasubstituted alkene. So this is the ease of formation of alkene if there is chances of reaction where trisubstituted and tetrasubstituted isomer are possible. At that time tetrasubstituted alkene prefers first. Simultaneously, if there is chances in reaction that disubstituted and monosubstituted product can be formed, at that time disubstituted alkene prefers predominantly. So this is the ease of formation of alkene, which is similar or same as the order of stability of alkene. The orientation or reactivity of elimination reaction follows stability of alkene, that is, more stable alkene forms predominantly in elimination reaction. After knowing Saytzeffs rule, we can predict which will be the major product in E2 reaction. Here is the general example where reaction between two halohexane with methoxide base. As we have 2 beta carbon, so if methoxide abstract hydrogen from this carbon, we will get 1 hexene, and if methoxide will abstract hydrogen from this carbon, we will get 2 hexene. And as Saytzeffs rule, major product is the one which have greater number of alkyl substituent. So 2 hexene is major product or Saytzeffs product. Here is a general reaction, and when this reaction actually performed using 2 iodohexane, 2 bromohexane, 2 chlorohexane and 2 fluorohexane, percentage yield of 2 isomer obtained is given. In iodo, bromo and chloroalkane, preferred product is 2 hexane, which is Saytzeffs product, while in fluoroalkane major product is 1 hexene. Here it is actually Hofmann product. Fluoride react with Hofmann orientation, which is the variable of E2 transition state. What is Hofmann rule? Whenever there is a possibility of formation of 2 alkene by elimination, the formation of less substituted alkene is favored. Hofmann elimination reaction is when a quaternary ammonium hydroxide is heated strongly up to 125 or higher degrees Celsius. It decomposes to yield water, a tertiary amine and alkene. Here is the example where sec-butyl trimethyl ammonium hydroxide upon heating liberates water and tertiary amine and gives alkene 1-butene as major product and 2-butene as minor product. Mechanism is similar with E2 mechanism, where abstraction of hydrogen and removal of leaving group in single step. As in Hofmann Rule, less substituted alkenes favor. Basis is that the least sterically hindered beta hydrogen is removed by base in this reaction. As we can see, beta carbon here has 2 hydrogen while this beta carbon has 3 hydrogen. Now this beta carbon is terminal carbon, so hydrogens are less sterically hindered and therefore base abstract hydrogen from this carbon. The regioselectivity of Hofmann elimination is opposite to that predicted by Saytzeffs rule. We have seen in Saytzeffs rule, hydrogen is preferentially abstracted by base from carbon which have fewer number of hydrogen. In Saytzeffs rule, base abstract hydrogen from this carbon, where we are getting 2-butene as a major product, which is more substituted alkene. But in Hofmann rule, hydrogen is abstracted from carbon, where hydrogen are least hindered. Therefore, here base is abstracting hydrogen from this terminal carbon. The variable E2 transition state. We have already seen E2 is concerted reaction, so both reactants are participating in transition state. Here is the example of alkyl iodide, where in transition state both carbon hydrogen and carbon iodide bonds are broken to a considerable extent. So at that time the transition state is more like alkene character and it prefers Saytzeffs orientation. Another type of transition state where alkyl halide is alkyl fluoride. We know carbon fluorine bond is much more stronger than carbon iodide bond. So for this E2 transition state, carbon fluorine bond will not break with same extent with carbon iodide bond. As base is abstracting this hydrogen, there is partially bond making and here is partially bond breaking process is there. In same time there is also breaking of this carbon fluorine bond, but carbon fluorine bond is more stronger, so extent of breaking is slower than carbon hydrogen bond breaking. So at that time partially negative charge is accumulated to this carbon, causing carboanion like transition state. And we know methyl anion is most stable and tertiary carboanion is least stable. So as stability of carboanion, base will abstract hydrogen from least substituted carbon, which is preferred Hofmann orientation. We have also another transition state which is carbonium like character, where base is not participating in particular transition state. This we will see in E1 elimination mechanism. E2 mechanism stereochemistry has anti-periplanar transition state. In E2 elimination, the new pi bond is formed by overlap of carbon hydrogen sigma bond with carbon halogen sigma star antibonding orbital. Normally, we are representing molecule in 2D. 3D molecule is represented with dashed and wedged bond. Dashed bond indicate bond is below the plane and wedged bond means bond is above the plane. To make pi bond, best overlapping is achieved when pi bonding and pi star antibonding orbitals have to lie in the same plane, and for this there are only two conformations which allows this. To study conformation, we have new representation of molecule which is Newman projection, where this carbon-carbon bond lies with I site. Conformation is also studied where molecule is also projected as Sauer's projection. Here is the representation of anti-periplanar or staggered conformation, which is more stable because bulky groups are far apart in this staggered conformation than this eclipsed conformation. As we can see here, this methyl group which are bulky are more nearer with each other in eclipsed conformation, while in staggered conformation they are away. So here is more steric repulsion while here is least steric repulsion. So staggered conformation is more stable than eclipsed conformation. Therefore, only anti-periplanar conformation bonds or orbitals are truly parallel. So E2 elimination accomplishes with anti-periplanar on transition state. E2 stereochemistry can be stereoselective. For this, we have to see E2 elimination reaction where base has choice to remove one of two hydrogen bonded with the carbon. We have an example of 2-bromobutane which is reacted with ethoxide base. Here we have 2 beta carbon. If base will abstract hydrogen from this beta carbon, we will get 2 butene, and if base will abstract hydrogen from this beta carbon, we will get 1 butene. 2 butene is major product or Saytzeffs product as it is more substituted alkene. But whether it is trans 2 butene or cis 2 butene, we cannot judge that. To see what will be the geometrical isomerism in our product, we have to see reactant. Two types of arrangement are seen of 2-bromobutane. However, better representation of various group arrangement is seen in Newman projection, where both sigma bonding and antibonding orbital lies in same plane. Which Newman projection is more stable? We can see here these methyl groups are far apart, while in this projection these methyl groups are nearer to each other. So here is more steric hindrance. So this is least stable and equilibrium favored toward this projection. Here two methyl groups are anti-periplanar, so less hindered, and so this arrangement exists predominantly. What happened where base abstract hydrogen? Here in stable projection, base will abstract this hydrogen, while in least stable projection, base will abstract this hydrogen, and we are getting particular product. Here abstraction of hydrogen gives this alkene. Now here both alkyl group or methyl group are on opposite side, so it is transalkene, and here alkyl group are on same side, so it is cisalkene. As this projection exists predominantly, we will get trans isomer predominantly as major product of 2-butene. So here is the example where this base have choice to remove one of two hydrogen from beta carbon, as here possibility of two conformational isomerism. One of the conformation exists predominantly. Base have choice to abstract this hydrogen predominantly, and thus we are getting only one isomer as major product. Any reaction in which only one of set of isomer is formed exclusively from all possible isomer is called stereoselective reaction, and here only trans isomer formed predominantly from possibility of both cis and trans isomer. This reaction is called as stereoselective reaction. So E2 stereochemistry can be stereoselective in nature. E2 stereochemistry can be stereospecific. For this, we need to see E2 elimination reaction where base has no choice to remove hydrogen. That means only one hydrogen is bonded with beta carbon. Here we have an example like this, which is 1-bromo 1,2-diphenyl propane. When it is reacted with sodium hydroxide abstract hydrogen from beta carbon. In our example, here is alpha carbon connected with halogen, adjacent carbon where only one hydrogen is there. In another side of alpha carbon, phenyl group is there. So here is only one beta carbon which has hydrogen, and there is only a single hydrogen is there. So our base have no another choice to remove hydrogen because there is only a one beta hydrogen is there. So base will abstract hydrogen from this carbon, and we will get a double bond over here. So there is formation of only a one single product. But is it trans or cis or both? For this, again we have to see the conformation of reactant. As reactant have two chiral center, so four type of stereoisomer are possible. But for E2 reaction, the essential requirement is carbon bromine antibonding and carbon hydrogen bonding orbitals needs to lie in same plane. This criteria is possible only in two diastereomer, that is diastereomer A and diastereomer B, where this CH and CBr bond lies in same plane. Now if we have diastereomer A, then when it will react with sodium hydroxide. This base abstract hydrogen from this beta carbon and we will get this type of alkene where phenyl groups are opposite side. While in diastereomer B, when base abstract hydrogen, we will get this type of alkene where phenyl groups are in same side. So more clearly, diastereomer A gives trans product and diastereomer B gives cis product. Stereospecific reaction is any reaction in which the stereochemistry of the product is determined by the stereochemistry of starting material. In our example, trans isomer is formed by one diastereomer, while cis isomer is formed by another diastereomer. So, stereochemistry of our product is determined by stereochemistry of starting material. That is, our diastereomer A only gives trans product, diastereomer B only gives cis product. Is called stereospecific reaction and hence E2 reaction can be stereospecific where base has no choice to remove hydrogen. Order of reactivity of alkyl halide in E2 mechanism. We have reactivity study where different kind of alkyl halides are reacted with same base ethoxide ion which gives various kind of product. Here we have the example of alkyl halide, that is primary, secondary and tertiary alkyl halide. Upon these reactions, various kind of alkyl halide reacts with different reactive rates. The most reactive is tertiary alkyl halide, then secondary alkyl halide, and finally the least reactive alkyl halide is primary alkyl halide. Now, what will be the reason for this? We have two reasons. First one is probability factor. It is a chance for the abstraction of hydrogen from alkyl halide. The more number of beta hydrogen present in alkyl halide, there is high chance to abstract them by base, and therefore high is the probability factor. In these examples, primary alkyl halide have only 2 beta hydrogens, while in secondary alkyl halide there is 3 and 3, 6 beta hydrogens, and finally in tertiary alkyl halide we have 9 beta hydrogen. So number of beta hydrogen is more in tertiary alkyl halide, so there is high probability factor for tertiary alkyl halide and high is the reactivity. Second reason is activation energy. It is energy to proceed the reaction. The more stable the product, more stable is transition state and less is activation energy, and so the rate of reaction is higher. The product which is obtained from different alkyl halide is monosubstituted and disubstituted, and we know disubstituted alkene is more stable than monosubstituted alkene, and this disubstituted product is obtained from tertiary alkyl halide. So in the reaction of tertiary alkyl halide, activation energy is less than we have reactant that is secondary or primary, and therefore there is high reaction rate when we are using tertiary alkyl halide for elimination reaction. Thus reactivity order of alkyl halide is tertiary, then secondary and then primary. Now it's time to study second elimination mechanism, E1 mechanism. In this mechanism, the first step is removal of leaving group. This leaving group, that is halide, takes bonding electron and leaves as negatively charged and forms carbocation intermediate. In second step, base will abstract this hydrogen where the bonded electron are transferred to carbon, which gives alkene as product. From this two step, first step is slower than second step. In first step, leaving of halide ion and formation of carbocation. In second step, abstraction of beta hydrogen by base and formation of alkene. As slower step is rate limiting step, and here it involves only one substrate, that is alkyl halide. Now how will we draw potential energy diagram? We have two step, so there is two transition state is there with intermediate carbocation. The slower step is a rate limiting step, so it is important for kinetic, and we will see the transition state for this step. In this first step, there is breaking of CX bond, so it is represented in transition state by partially breaking bond, where halide gets delta negative charge and delta positive charge on carbon. What will be the kinetic of E1 mechanism? In rate limiting step, we have only one reactant which is involved in rate limiting step, and in transition state there is only involvement of one reactant which is alkyl halide. So rate depend only on a single reactant, so it is unimolecular elimination reaction. It is E1 reaction, and as one reactant involved in rate limiting step, it follows first order kinetic. Evidences in E1 reaction, we have two steps, where in first there is formation of carbocation, and in second step there is CH bond breaking. So to prove that, we need to study the kinetic, whether it follows first order kinetic. For carbocation, whether it is accomplished by rearrangement, and order of reactivity is same as SN1 reaction. The next is not accomplished by a primary hydrogen isotope effect. First evidence is a reaction follow first order kinetic. Experimental data shows that a reaction rate depends only on one reactant, which is alkyl halide, so it is first order kinetic reaction. Second evidence, it is not accomplished by primary hydrogen isotope effect. We have seen in rate limiting step there is involvement of only one bond, which is carbon halide bond. As rate limiting step only involve breaking of CX bond, this carbon hydrogen bond has no participation in reaction rate. So carbon hydrogen or carbon deuterium bond have no influence on rate of reaction. So E1 reaction is not accompanied by a primary hydrogen isotope effect. We have seen in detail this effect in E2 mechanism. Reactivity of alkyl halide toward E1 mechanism. Slow step is a rate determining step where we are obtaining carbocation intermediate. So, reactivity depends on the stability of carbocation. We know the stability of carbocation where tertiary is most stable, then secondary, then primary, and then methyl carbocation. Now, how we will get this type of carbocation? Normally, carbocation produced by alkyl halide reactant where tertiary alkyl halide gives tertiary carbocation. We can see over here, this is the general structure of alkyl halide. If tertiary alkyl halide is there, removal of this halogen gives a carbocation which is also tertiary one, and likewise secondary alkyl halide gives secondary carbocation, primary gives primary carbocation. Now from methyl to tertiary carbocation, stability of carbocation will increases, and therefore energy needed to form carbocation is lesser, and therefore rate of reaction will increase from methyl to tertiary when we are using methyl halide to tertiary alkyl halide. So the reactivity of alkyl halide for E1 reaction is tertiary alkyl halide is most reactive than secondary alkyl halide. Secondary is more reactive than primary alkyl halide. One of the important things, as we are getting carbocation intermediate, rearrangement of carbocation also diverges the type of product formation, which we will see later. Orientation of E1. When tert pentyl bromide is reacted with ethanol, what will be the product? Here we are getting two structural isomer, 2-methyl butene and 2-methyl 2-butene, where 2-methyl 2-butene form as a major product. So the reaction is regioselective, and so strong Saytzeffs orientation where most stable alkene here is tri-substituted alkene is preferred as predominant over this di-substituted alkene. Mechanism where step 1 is removal of leaving group which gives 2-pentyl carbocation. In second step, which is abstraction of hydrogen. Now what are the available beta hydrogen? We can see we have 3 beta carbon where these 2 are primary carbon and here is the secondary carbon. So we have two type of beta hydrogen, either this hydrogen or this hydrogen can be removed by base. So we have two type of pathway, those gives structural isomer. Pathway 1, that is abstraction of secondary hydrogen, gives tri-substituted alkene as major product, and abstraction of this primary hydrogens in pathway 2 gives di-substituted alkene as minor product. Here more abstraction of beta hydrogen from carbon 3 occurs as it gives more stable alkene as product. This can be better understood by reaction coordinate diagram, where this carbocation on next step converted into alkene, tri-substituted alkene is more stable than di-substituted alkene, and the transition state for generation of more stable alkene has lower energy, so it is more preferable. Rearrangement of carbocation in E1, carbocation intermediate is formed which is highly reactive and unstable, and we know the stability of carbocation, where tertiary carbocation is most stable, then secondary, and then primary, and this stability order of carbocation causes rearrangement in carbocation structure, and hence diverse type of alkene formation observed in E1 reaction. Now, why tertiary carbocation is most stable than secondary, and secondary is more stable than primary, and lastly methyl carbocation is least stable? The reason is inductive effect. The electron releasing inductive effect of alkyl group reduces positive charge by transferring electron density toward carbocation, an electron deficient species. The more number of alkyl group attached to carbocation, the more is the stabilization of carbocation, and therefore tertiary carbocation is most stable and methyl carbocation is least stable. Let us see example of rearrangement. The first example, where 3-methyl 2-butyl tosylate is reacted with an butanol. Here TS indicate tosyl means para-toluene sulfonic acid. Now what will be the major and minor product? 2-methyl 2-butene and 3-methyl but1-ene. Apart from these two products, in the reaction third product is also observed, which is 2-methyl but1-ene. The product is double bond formation other than alpha beta carbon. Okay, alpha beta carbon, where here there is first product is observed. Here we have 3-methyl but1-ene. We have the third product where double bond we can say on beta gamma carbon. Second example, where 2-bromo 2,2-dimethyl butane is reacted with ethanol. What will be the product? Here also diversion of product, where alkene generated from substrate lacking of beta hydrogen and alkene formed with diverse skeletal. From the above example, we can see deviation in products formation proves rearrangement of carbocation intermediate. And what will be the direction of rearrangement? It depends on stability of carbocation from unstable to stable direction. Let us see the mechanism of first example. In first step, there is a removal of leaving group which gives carbocation. Then abstraction of beta hydrogen by base. In our example, we have two beta carbon, means two type of beta hydrogen is there. Here is primary and here is tertiary. So depending upon abstraction of hydrogen, we will get two type of product. 3-methyl 1-butene when base abstract primary hydrogen. 2-methyl butene while base will abstract this tertiary hydrogen. When we look up the structure of intermediate, here is secondary carbocation. Adjacent carbon from this secondary carbocation is the tertiary carbon which contains carbon-hydrogen bond. So if this hydrogen shifting is possible, it gives tertiary carbocation which is more stable than secondary carbocation. This is called as a rearrangement, which is 1-2 shift conversion of secondary to tertiary carbocation. Here carbon hydrogen bonding electron are taken up by this hydrogen, and this hydrogen use this bonding electron to form sigma bond with this carbon, and simultaneously this carbon, as electron is taken up by this hydrogen, it gets positive charge. So we can see also the transfer of charge from secondary carbon to tertiary carbon. We are getting from this 1-2 hydrogen shifting secondary carbocation to tertiary carbocation, and tertiary carbocation is more stable than secondary carbocation. So this type of arrangement is possible or favorable. As in reaction mixture base is there, here we have this 2 beta carbon and here is the third beta carbon. So our base have choice, either it abstract hydrogen from these primary carbons or hydrogen from this secondary carbon. So here also we are getting two type of product, where abstraction of hydrogen from secondary carbon gives 2-methyl butene, and abstraction of hydrogen from this primary carbon gives 2-methyl butene. Here we are getting a product 2-methyl butene, where this double bond is on beta gamma position with respect to starting material, which is resulted by rearrangement of carbocation. In second example, the same way rearrangement of carbocation is there, where in first step removal of this leaving group gives secondary carbocation, and then because of rearrangement we are getting product which have diverse skeletal from starting material. How it will take place? As in previous example we have seen 1-2 shift. Here also the shifting of positive charge from this carbon to here gives tertiary carbocation which is stable than secondary carbocation, and this rearrangement is due to 1-2 methyl shift conversion of secondary to tertiary carbocation. Methyl group takes both bonding electron, so this carbon becomes positively charged, and methyl group simultaneously form bond between this carbon, where it gives an electron and there is removal of this positive charge. So ultimately it is transfer of this charge from this carbon to here, which gives tertiary carbocation, and then abstraction of hydrogen from any of this beta carbon gives particular product. Difference between E2 and E1 mechanism. We have seen subtopics of both mechanism, and from this we have differences between E2 and E1. First, molecularity, where E2 is bimolecular and E1 is unimolecular. Order of reaction: E2 follows second order kinetic, E1 follows first order kinetic. In mechanism, E2 is single step mechanism, E1 is two step mechanism, and likewise if only one step, it have only one transition state in E2, while in E1 it has two transition state. In evidences, E2 shows primary hydrogen isotope effect, while E1 shows rearrangement. Order of reactivity toward alkyl halide: it is tertiary, secondary and primary in both of mechanisms. In E2 it is because of stability of alkene, a product, while in E1 it is because of stability of carbocation intermediate. High concentration prefers E2 mechanism and strong base prefers E2 mechanism, while in E1 strong and weak both gives E1 mechanism and they do not have any influence on mechanism. Stereochemical aspects, where in E2 hydrogen and halogen must be on anti-conformation. Factors affecting elimination reaction. For this, we need to see important component of both the reaction mechanisms. In E1, rate limiting step is step 1, where we are getting carbocation intermediate. In E2, it is concerted reaction. Here are factors influences both the mechanism. We have seen substrate structure, where in E1 mechanism reactant is preferred, which gives most stable carbocation. Reactant prefers E2 mechanism, which have more number of beta hydrogen and which gives most substituted product. Good leaving group prefers both mechanisms. Base, where strong base prefers E2 mechanism. Solvents, polar solvent stabilize carbocation in E1 mechanism. Influence of substrate structure. We have seen order of reactivity of alkyl halide. For both E1 and E2, tertiary alkyl halide are most reactive and primary alkyl halides are least reactive. In E1 mechanism, reaction favored by tertiary alkyl halide, allylic and benzylic substrate because they provide stability to intermediate carbocation during reaction. Tertiary alkyl halide stabilize carbocation with inductive effect of alkyl substituent. In allylic and benzylic substrate, carbocation is stabilized by resonance effect. Normally, primary alkyl halides do not undergo E1 elimination reaction. Why? Because primary alkyl halide, if they follow E1 mechanism, they give primary carbocation which is least stable. So, primary alkyl halide usually do not undergo E1 mechanism. In E2, reaction favored by tertiary substrate because tertiary substrate provides more beta hydrogen for abstraction and it gives more substituted product. We have a reference for this. Leaving group. In both E1 and E2 reaction, leaving group dissociate in transition state. So, it affects to the rate of reaction. The weaker the carbon halogen bond, the better is its living ability. So it is element effect, and we know that carbon iodide bond is weakest bond from all carbon halogen bond. So this iodine is good leaving group for both E1 and E2. This factor is same in nucleophilic substitution reaction. Base have small effect in E1 mechanism. Base strength is unimportant as not participating in transition state. So normally solvent itself can also act as base in E1 mechanism. Examples are ethanol and water. In E2, reaction favored by strong base because base abstract hydrogen in rate limiting step. The rate of reaction will depend on strength of base or nucleophile. Examples are ethoxide and alkoxide anion. Solvents, where polar solvents like methanol and water stabilizes to charged species by intermolecular electrostatic interaction. We know in E1 carbocation intermediate a charged species is generated. So at that time polar solvent favored E1 mechanism by good ionizing power. Protic polar solvents stabilize the intermediate carbocation. Examples of this type of solvents are ethanol, methanol, water and acetic acid. In E2, solvents have small effect, but some reagents are stronger bases in less polar solvent. So aprotic, polar and non-polar solvents utilized. Examples are DMSO and DMF. Now it's time to see reactions of alkene. We have many named reactions of alkene: electrophilic addition, addition of hydrogen halide, free radical addition reaction where hydrogen halide is reacted with alkene in presence of peroxide, where we are getting anti-Markovnikov product. Hydroboration oxidation using boron hydrogen peroxide in alkali media. Ozonolysis, where ozone is reacted with alkene. Upon different condition, different type of product are obtained like carbonyl compounds, carboxylic acid, alcohols. Hydrogenation reaction, which is conversion of alkene to alkane. Halogenation, halogen is reacted which gives vicinal dihalide. It is saturation unsaturation test. Oxidation, which is Baeyer test using potassium permanganate oxidizing agent. Diels-Alder reaction, where alkene acts as dienophile reacted with diene gives cycloaddition product. First reaction, alkene reacts with oxidizing reagent also called as hydroxylation reaction or glycol formation, where manganate ion are a strong oxidizing agent oxidize alkene to cis-diol. This reaction is applied to detect unsaturation in organic compound called as Bayer's test, where if unsaturation present in any compound, this potassium permanganate, which is purple in color, converts to brown color manganese dioxide. In mechanism, first potassium permanganate react with alkene gives ester intermediate which on hydrolysis gives cis-diol. Electrophilic addition reaction. Why alkene undergoes electrophilic addition reaction? For this, we have to know what is the definition of electrophilic addition. In any mechanism of addition in which an electrophile first attacks to the multiple bond is called as electrophilic addition. General reaction where alkene is reacted with species where product with addition of H and Z. Now what is HZ? It's a hydrogen bonded with nucleophile. Here are examples where we have hydrogen chloride, hydrogen bromide, sulfuric acid, protonated water. Now what is electrophile and why it attacks to the multiple bond? We have both the reagent. If we see potential map of alkene and here HZ example is hydrogen chloride. In electrostatic potential map, electron rich region are represented as red color while electron deficient region are represented as blue color. So we can see here red color which is of doubly bond. So double bond in alkene is electron rich, while in hydrochloric acid there is blue color which indicate it is electron deficient region or electron poor region. So the double bond is electron rich region. In this species hydrogen is electron deficient region. Double bond is weaker than sigma bond as side to side overlap of p orbital. These pi electrons are loosely held by carbon nuclei. So carbon-carbon double bond serve as nucleophilic center available for electrophilic species, while in hydrogen chloride or hydrogen connected with nucleophile, it is polar molecule where hydrogen has delta positive charge, electron deficient region able to act as electrophile. So first step in electrophilic addition where addition of electrophile proton to carbon-carbon double bond, alkene gives its pi electron to proton and forms sigma bond with this proton by donating its pi electrons and formation of carbocation intermediate. Second step, when nucleophile attacked to electron deficient carbocation which gives addition product. Here first step is slow step, that is formation of carbocation. Examples where there is addition of sulfuric acid, alkene react with cold concentrated sulfuric acid to form alkyl hydrogen sulfate. They are delicate solids and are difficult to isolate. Reaction mixture is diluted with water and upon heating we will get alcohol. Acid catalyzed hydration where propene is reacted with protonated water which gives alcohol. Examples where ethene is reacted with hydrogen bromide which gives bromoethane. Now what will be the product where propene or 1-butene is reacted with hydrogen bromide? In first example we are getting only one product, but in both of below reaction we are getting two type of product. In propene we are getting 2 bromopropane as major product and 1 bromopropane as minor product. In butene, we are getting 2 bromobutane as major product and 1 bromobutane as minor product. So we can say that this reaction is a regioselective reaction. Here is the definition of regioselective reaction: a reaction that can produce 2 or more constitutional isomers but gives one of them in greater amounts than the other isomers. This regioselectivity of electrophilic addition reaction is explained by Markovnikov. So it is also called as Markovnikov's orientation. Markovnikov gave rule that when an asymmetrically substituted alkene reacts with hydrogen halide, the hydrogen adds to the carbon that has the greater number of hydrogen substituents, and the halogen adds to the carbon having fewer hydrogen substituents. We have unsymmetrically substituted alkene. Example is propene. Here in statement, hydrogen adds to carbon that has greater number of hydrogen substituent. This carbon have more number of hydrogen substituent. So hydrogen adds to this carbon. Halogen adds to carbon having fewer hydrogen substituent, and we have this sp2 carbon which have only one hydrogen substituent. So bromine adds to this carbon. Major product in electrophilic addition reaction is called as Markovnikov's product. Mechanistic basis for regioselectivity or proof for Markovnikov rule: upon reaction with hydrogen bromide, we have two type of pathway, where in pathway 1, if hydrogen adds to carbon which have more number of hydrogen substituent, it gives secondary carbocation, and upon addition of this bromide we are getting 2 bromopropane. In second pathway, if this hydrogen adds to carbon with less number of hydrogen, we will get primary carbocation intermediate. Now in second step, bromide adds to this carbocation which gives 1 bromobutane, which is minor product in particular reaction. We know the stability of carbocation, where tertiary carbocation is more stable than secondary and secondary carbocation is more stable than primary. So because of relative stability of this secondary carbocation favors pathway 1, so there is more formation of secondary carbocation and likewise more formation of this 2 bromopropane. So this product is major product. Attack of electrophile is always favored in direction which result in formation of more stable carbocation. So pathway 1 favors over pathway 2, and 2 bromopropane form predominantly through formation of more stable carbocation. We have a revised version of Markovnikov rule. The statement is: in the addition reaction of unsymmetrical alkenes, the attack of electrophile occur on that carbon bond which result in the formation of more stable carbocation. Reactivity of alkenes toward acids. Reactivity depends on stability of intermediate carbocation. Here we have series of examples. First we have to see which intermediate carbocation obtained from these reactants. Normally isobutylene forms tertiary carbocation. As hydrogen H2 this carbon and we will get carbocation on this carbon which is tertiary in nature. 1, 2, 3. These 3 examples 2 butene, 1 butene and propylene forms secondary carbocation. And here we have 2 examples which gives primary carbocation. Second thing, which reactant react faster depending on stability of intermediate carbocation. As we know, tertiary carbocation is stable, then secondary and then primary. So this isobutylene reacts faster than 2-butene, and likewise 2-butene or 1-butene and propylene which forms secondary carbocation reacts faster than ethylene. So this is our order of reactivity, where ethene is least reactive and isobutylene is most reactive. Now vinyl chloride is less reactive than ethylene. The reason is electron withdrawal by halogens intensify positive charge and destabilize the primary carbocation, and because of destabilization of carbocation it is difficult to get carbocation in vinyl chloride. So vinyl chloride is less reactive than ethylene. What happens when hydrochloric acid is reacted with 3,3-dimethyl 1-butene? As major product, according to Markownikoff Rule, hydrogen adds to carbon which have more hydrogen substituent. So 3-chloro-2,2-dimethylbutane is our major product and 1-chloro-3,3-dimethylbutane is minor product. But when we are going to actually perform this reaction, 3-chloro-2,2-dimethylbutane will be not our major product, and there isn't any formation of 1-chloro-3,3-dimethylbutane. Actual products which are formed are 3-chloro-2,2-dimethylbutane as minor product and 2-chloro-2,3-dimethylbutane as major product. So this is rearranged product of haloalkane. Why we are getting rearranged product? For this we have to see mechanism, where first, as hydrogen adds to carbon which have more number of hydrogen, we will get secondary carbocation intermediate, and upon addition of this chlorine we are getting 3-chloro-2,2-dimethylbutane. Now what happened? As this secondary carbocation adjacent carbon is quaternary in nature, so there is chances of 1,2-methyl shift. This is rearrangement where there is 1,2-methyl shift, where shifting of this methyl group from quaternary carbon to carbocation results in formation of tertiary carbocation, which is more stable than secondary carbocation. So rearrangement happens from less stable to more stable carbocation. Now when chlorine adds to tertiary carbocation, it gives 2-chloro-2,3-dimethylbutane as major product. Carbocation is rearranging from secondary to tertiary, so it is the example of carbocation rearrangement in electrophilic addition reaction. Normally, when propene reacts with hydrogen bromide, major product is 2-bromopropane. But when this reaction performed in presence of peroxide, at that time major product which we are obtaining is 1-bromopropane. So in absence of peroxide, major product is Markovnikov product, while in presence of peroxide, major product is anti-Markovnikov product. This change in regioselectivity because of peroxide is called as peroxide effect or Kharas effect. As this reaction performed in presence of peroxide under heat or radiation, it is free radical addition reaction and it is the example of anti-Markovnikov orientation. Mechanism of peroxide effect, where first is homolytic cleavage of peroxide which gives alkoxy radicals. In second step, alkoxy radical reacts with hydrogen bromide which liberates bromine radical. Third step, in this step, bromide radical reacts with alkene. It can attach either these carbon which have more number of hydrogen in pathway 1 which gives secondary radical. Bromine radical can also attach with this carbon which have only one hydrogen in pathway 2 which gives primary radical. Which pathway more prefer, pathway 1 or pathway 2? For this we have to see stability of radical, which is tertiary radical is more stable than secondary and primary. So as pathway 1 gives secondary radical which is more stable than primary radical, reaction favors pathway 1. Fourth step, that is addition of hydrogen atom to form anti-Markovnikov product. Anti-Markovnikov addition is addition reaction for which the regioselectivity is opposite to that predicted on the basis of Markovnikov rule, and the product which is formed is called as anti-Markovnikov product. Next reaction is hydroboration oxidation. It is conversion of alkene to alcohol using boron hydride or boron and hydrogen peroxide. Usually this reaction have two-step sequence. First is hydroboration stage, where boron adds to alkene to give alkyl boron. Second is oxidation stage, where alkyl boron is oxidized with hydrogen peroxide to give an alcohol. Boron, it can be simple boron or substituted with alkyl group is called as alkyl boron. Alcohol which is formed is anti-Markovnikov orientation with syn stereochemistry, which means syn addition of two substituents to the same side, or we can say as same phase of double bond. Boron, if we see the structure of boron, there is no complete octet. So, boron have a strong tendency to acquire an additional electron pair. Normally, two boron combine which gives diboron structure, which is dimer, a flammable, toxic and explosive gas. Now, what is in a structure of dimer? Two boron atoms share two electrons in a hydrogen-boron bond by means of unusual half bonds, which are three-centered banana-shaped bonds. For detail, you may go through reference chemzipper.com. When boron dissolves in tetrahydrofuran, a complex is generated which is boron tetrahydrofuran complex, which is more convenient and less dangerous reagent than diboron. Example where 1-methyl cyclopentene upon hydroboration oxidation gives trans 2-methyl cyclopentanol. Here we can see both hydrogen and hydroxy group are on same side. So it is syn addition. Mechanism where first stage is hydroboration of alkene. It is concerted step where boron accepts pi electron, where boron is electrophile and adjacent connected hydrogen is nucleophile. Alkene shares its pi electron with boron and gives organoboron intermediate. Second type of possibility where boron adds to this carbon which is more substituted, we may get this kind of product. But practically this kind of product is not observed in this reaction. To see a reason, we have to check possible transition state of both chances. First, where boron bond making with less substituted carbon, where there is delta negative charge over boron, and as this hydrogen cannot form bond with this carbon with same extent as boron, delta positive charge generated over this more substituted carbon. In second chance where boron forms bond with more substituted carbon, in transition state there is a representation of partial bond forming where boron have delta negative charge, and as we have seen in first chance, there is delta positive charge generation to adjacent carbon which is partially forming bond with this hydrogen. Here we can see that delta positive charge is generated on carbon which is more substituted, and here delta positive charge is generated to a carbon which is less substituted compared to this transition state. And as delta positive charge is generated to more substituted carbon, this transition state is more stable where delta positive charge on tertiary carbon. Here transition state is less stable transition state because delta positive charge is generated on secondary carbon. Why this is more stable transition state? Because this delta positive charge is stabilized by these alkyl substituents which are more in this carbon than this second carbon. So this second chance is not observed in hydroboration oxidation, and we only get this product. We can see regioselectivity. Boron adds to less substituted carbon and hydrogen adds to more substituted carbon. Here is the explanation of our previous slide. Second stage, that is oxidation stage. In first step, hydrogen peroxide is converted to its anion form in basic solution, where hydrogen is abstracted by hydroxide ion, which gives peroxide anion. Second step, nucleophilic attack of peroxide anion to boron, which forms boron-oxygen bond. In third step, carbon migrates from boron to oxygen, where there is formation of alkoxyborane. In fourth step, it is hydrolysis. Cleavage of boron-oxygen bond gives alcohol. Ozonolysis. It is ozone-induced cleavage of carbon-carbon double or triple bond. Here, ozone acts as powerful electrophile. Solvents which are used in ozonolysis must be unaffected by ozone. Some of the examples like chloroform, carbon tetrachloride, petroleum ether are used as solvents. In ozonolysis, we are getting oxygen containing functional groups depending upon various reactants. Ozone, when react with alkene, first it gives ozonide intermediate, which upon reaction with water or dimethyl sulfide gives carbonyl compounds. If ozonide reacted with hydrogen peroxide, it gives carboxylic acids, while with sodium borohydride it gives alcohols. In this reaction, zinc is used to destroy side product of hydrogen peroxide because these have tendency to further oxidize these carbonyl compounds into carboxylic acid. This is the reaction of 1,3-dipolar cycloaddition. Mechanism where in first step ozone interact with alkene and gives cyclic intermediate molozonide. This step is 1,3-dipolar cycloaddition. It is cycloaddition because it gives cyclic intermediate. But why it is 1,3-dipolar? It is because we have a 1,3-dipole which is ozone. Here in mechanism, positive and negative charge present in adjacent oxygen, but we have a resonance structure where ozone have positive and negative charge on oxygens which are separated by another oxygen atom. So it is 1,3-dipole. It is the example of 1,3-dipole, and a reaction of 1,3-dipole is a 1,3-dipolar reaction. So it's a 1,3-dipolar cycloaddition step. Here, one of the oxygen of ozone behaves like electrophile, interact with this pi electron and makes sigma bond, while another terminal oxygen act as nucleophile interact with this sp2 carbon and makes bond. This molozonide intermediate is highly unstable, so it readily breaks into carbonyl compound and reactive intermediate. It's a reverse 1,3 dipolar cycloaddition step. Now for step 3 we need to rotate this carbonyl compound 180 degree. So we will get this type of arrangement of intermediates. Negatively charged oxygen act as nucleophile and attack to this carbonyl carbon, which gives ozonide intermediate, and it is step 3, which is 1,3 dipolar cycloaddition. Now depending upon various other reactant, ozonide gives different kind of product. Here is the example of water where it gives carbonyl compound. Here is explanation of all steps. What will be the product where 2-hexene reacted with ozone and then water and zinc? In alkene we have two alkyl group. Here is a red one and here is blue one. So upon ozonolysis, breaking of this double bond and incorporation of oxygen over here, we are getting two type of aldehydes. In second reaction, where 2-methyl-2-pentene is reacted with the same reagents, one of the part of alkene, one side of alkene contains two methyl group. So here incorporation of oxygen gives ketone, which is acetone, and here in second side ethyl group is there, and here is the sp2 carbon gives propanol. Now what will be the product of third reaction where 2-methyl-2-butene is reacted with first ozone and second reagent is hydrogen peroxide. Alkene and ozone gives ozonoid, and then ozonoid upon reaction with peroxide gives carboxylic acid. First part we are getting here, that is acetic acid, but here because it is disubstituted we only get propanone. Addition of halogen to alkene, where addition will give vicinal dihalide. Vicinal means halogens which are connected with adjacent carbons, while if same carbon contains two halogen it is called as geminal dihalide. It is anti-addition of halogen to alkene. In first step of mechanism, where this electron-rich region of alkene double bond attacks to one of the bromine atom and there is formation of cyclic intermediate with bromonium ion. In second step, this bromoanion attacks to carbon which gives dibromoalkane. Example of reaction where 2-butene when reacted with bromine it gives 2,3-dibromobutane. This product have two chiral center, so product obtained as 4 stereoisomers, where one of the pair of enantiomer and other pair of mesomers. This is the example where we prove reaction of alkene with bromine can be stereospecific and stereoselective. Which isomer is formed is also depends on isomerism of alkene. Here is the example where hydrogen are on same side. That means in cis butene, when it is reacted with bromine, we will get pair of enantiomers. And while hydrogens of alkene are on opposite side, means transalkene is reacted with bromine, at that time we will get pair of mesomers. Stereoselective reaction is any reaction in which only one set of stereoisomer is formed exclusively from all possible isomer. So, if we separately do addition reaction of halogen with cis alkene, at that time we are getting only one set of stereoisomers. So cis only gives enantiomer while trans only gives mesomer. In trans alkene we are not getting enantiomers, only we are getting mesomer. So at that time only one set of stereoisomer is formed exclusively from all possible isomer. So this reaction is stereoselective reaction. Stereospecific reaction is any reaction in which the stereochemistry of product is determined by stereochemistry of starting material. As in our example, mesomer formed because we have trans stereochemistry of alkene, and enantiomer is formed because starting material have cis stereochemistry. We can also say if we choose cis alkene or cis butene, we will always get enantiomers, while if we choose trans alkene, we will get mesomers. So here stereochemistry of product is determined by stereochemistry of starting material. So this reaction is also stereospecific reaction. Next reaction is halohydrin formation, where halogen is reacted with alkene. In presence of water, we will get halohydrin, where carbon containing halogen, adjacent carbon contains hydroxide group. Example where ethene is reacted with chlorine and water as solvent, which gives ethylene chlorohydrin. Mechanism in first step, as in electrophilic addition of alkene, this halogen adds to sp2 carbon and formation of carbocation. This positive charge is stabilized by adjacent halogen, which gives halonium ion. As in reaction mixture water is there, this water attacks to this carbon and gives this type of intermediate. Now this negatively charged halide ion abstract one of the proton of this positively charged species, which gives main product. Reaction of propene with bromine gives bromonium intermediate, which react with water and gives 1 bromo propane to all. Here one of the chances is there, either this water adds to second carbon, we will get this product. If this water adds to this carbon, so the product is different, but exclusively we are getting 1 bromo propane to all, where hydroxide ion is attached with this carbon number 2. It is because of stability of transition state. More stable transition state is when where this hydroxide group adds to this second carbon, because In transition state, this carbon partially get positive charge, and we know stability of carbocation where tertiary is more stable than secondary and secondary is more stable than primary. So this transition state is more stable because delta positive charge occupied by secondary carbon, while here partially positive charge is occupied by primary carbon. So hydroxide group always adds to carbon depending upon stability of carbocation. Free radical substitution reaction. Alkene upon reaction with halogen gives addition product, while alkane upon reaction with halogen gives substituted product. So addition reaction is characteristic of alkene and free radical substitution reaction is characteristic of alkane. However, alkene have alkyl substitution, means alkane part is also there in alkene. So at that time this alkene like group have susceptibility for substitution reaction, and here alkene which gives addition reaction. So in alkene both addition and substitution reaction site is there. Therefore, beside this addition reaction which is characteristic of alkene, alkene may undergo free radical substitution reaction. When propene is reacted with chlorine gas at low temperature, we will get 1,2-dichloropropane, an addition product, where there is heterolytic addition, means chlorine breaks heterolytically. However, if the same reaction is performed at higher temperature, at gas phase, 2-chloropropene is formed, which is substituted product, where there is free radical substitution, chlorine breaks homolytically. Mechanism: at high temperature, chlorine breaks homolytically, which gives chloride radical. This chloride radical interact with sp2 carbon and form bond, which gives a radical on second sp2 carbon. So there is formation of a radical intermediate. Now this radical intermediate interact with chlorine gas and gives addition product. So it's the mechanism of free radical addition. Here the step 1 is reversible. Alkene react with chloride radical, and in step 2 this radical react with chlorine gas. Now if the temperature is high, majority of the chlorine gas is converted into radical. Therefore at high temperature this radical will not readily get chlorine gas. So at high temperature majority of this radical converts into starting material rather than this forward addition reaction. In second reaction, chloride radical interact with this hydrogen, which gives hydrochloric acid and allyl radical. In next step, allyl radical interact with chlorine gas and gives allyl chloride and chloride radical. It's a free radical substitution. This allyl radical is stable than this first radical. Therefore, this allyl radical can wait for chlorine to forward the substitution reaction. Whichever temperature is there, either at high temperature or low concentration of chlorine. Because this allyl radical is stable than this radical, it waits to get chlorine gas and interact with chlorine gas and gives allyl chloride. Therefore, substituted product absorb more than addition product. H. C. Brown explained this reaction as low concentration of halogen can be used instead of high temperature to favor substitution reaction on allylic carbon. N-bromosuccinimide, which is known to be a source of bromine. It is used to brominate allylic carbons because it provides a constant low concentration of bromine. As each molecule of hydrogen bromide is formed by halogenation, NBS converts it into bromine. Detailed mechanism, orientation and reactivity of free radical substitution. We have a concept of allylic and vinylic hydrogen. Vinylic hydrogens are the hydrogen which are attached to sp2 hybridized carbon of alkene, while allylic hydrogen which is attached to carbon adjacent to double bond. Example of the free radical substitution reaction where propene reacted with bromine on presence of light or heat in gas phase gives 3-bromopropene. Mechanism, as it is free radical reaction in initiation step, bromine gas breaks homolytically, gives free radical bromide. This radical react with allylic hydrogen and gives allylic radical. Then allylic radical reacts with bromine and gives allyl halide or allyl bromide. Termination step, when two radical species makes allyl bromide. Ease of extraction of hydrogen atom in this reaction, which is reactivity of hydrogen for substitution reaction, is allylic is most reactive, then tertiary, then secondary, then primary, then methyl radical, and lastly then vinylic hydrogen is least reactive. It is similar with stability of free radical, where allylic radical is most stable and vinylic radical is least stable. Allylic system is more stable than tertiary carbocations too is because of resonance, as doubly bonded carbon are sp2 hybridized, radical is also sp2 hybridized. So if radical is present on adjacent to double bond, there is resonance or moving of electron is possible, which gives resonance. Now we will see allylic rearrangement. For this we have an example where 1-octene reacts with NBS, which gives 3-bromo-1-octene. We know NBS is used to add bromine to allylic carbon. However, we are getting another product which is 1-bromo-2-octene, a rearranged product obtained with larger amount. Here allylic hydrogen is only present on carbon number 3. Thus radical formation only possible at this carbon, but a rearranged product reveals the radical formation is also possible at carbon number 1, as in this product bromine adds to carbon 1. Let's see mechanism for this resonance stabilization of allyl radical. Here are reactant where bromide radical react with this hydrogen which gives allyl radical. This radical is reactive intermediate, so it try to stabilize. Adjacent to this radical is double bond, so shifting of this double bond gives one of the resonance contributing structure, and therefore here is the stabilization by resonance. Here is the resonance hybrid. The resonance phenomena in allylic system is called as allylic rearrangement. Now here we are getting two of the site for attack of bromide radical. If bromide radical attack to this side B, we will get this product, and if bromide radical attack to this site A, we will get this product where bromide adds to carbon 3. End of the topic of alkene, where major references are Organic Chemistry by Morrison and Boyd, Organic Chemistry by Collier Bruce, Organic Chemistry by Francis A. Corey, Organic Chemistry by Mehta and Mehta. You may also see references of each slide at the bottom of every slide. Thank you.